All right. Good morning, good day. Oh, Cole would like to say hello. Hello, Cole. All right. So for now, what we will do is we will look at exact equations, right? And for exact equations, again, there is a level of setup that you need to do. But in this case, I feel that the solution will be a bit more complicated, or rather, it's a bit more confusing, right? It's not complicated. It's just going to be confusing, right? So before we even begin, right, what you need to do if you want to see if your equation, if your differential equation fits the criteria of exact equations, is you need to order it like this. And again, right, this needs to be the format, right? No other formats are available, right? What you might do is something like this. This is not going to be a good format, or this is not a format for exact equations. What you need is basically a term, right? A term that is stuck to a dx, and then another term that is stuck to a dy. And then you have to add them. Again, right? If drawing boxes is going to help, right? Go ahead, draw the boxes, right? If going, I don't know, if making parentheses or if giving stuff parentheses will help, then please, by all means, start with that, right? But for now, we need to order it in this form. M dx plus n dy is equal to 0. M in here could be any kind of expression, so could n. The thing now is that for us to be able to tell if they are good for exact equations is this. The partial derivative of m with respect to y, aka the thing that is not what it's stuck to, is equal to the partial derivative of n with respect to x, which is the thing that it's not stuck to, right? So in this case, what we're doing here is deriving with respect to the other variable. And this deriving stage is very important. This is first and foremost the checking stage to see if it is fit for exact equations. If it is, then you can proceed with the rest of your with the rest of your solution. For the next one, right? For the next step, what you can do is either integrate either m with respect to dx or n with respect to dy. So you literally are going to do what is being asked in here. Either you do this or you do this. But do not do both. I mean, you can do both. But in this case, what you want to do is just pick one. Once you've done that, you will now again derive with respect to the other variable. So this might seem very weird. Say for example, we're choosing, right, m dx. What you're going to have to do now is you're going to have to derive that with respect to y, right? Why are we doing this? Why are we taking like so many winding roads? It's because we want to be able to make sure that we are getting the correct answer. Or on the other hand, if you have selected n dy, right, the integral of n dy, you will now derive that with respect to x, basically the other variable, right? And what is happening here is basically we're just checking to see if we are missing any terms. And for the last one, there will be another integration. So first, right, we check, right? Let me move this a little bit, right? Check using this thing, right? And then either integrate this or this, right? And then derive it with respect to the other variable, and then, right, integrate to find excess, right? I'll just say it's excess. It's better to explain if I show you the solution. Say for example, something like this, number 1. Right? It's 5y squared plus 6x times dx plus, and that is very important, the plus should be a plus in here, plus 10xy minus 4 dy. So very clearly, because of the color coding here, we can see that this is your m, because it's stuck to the dx, and then this is your letter n, which is stuck to your dy. So let's now check for our variable, right? We're going to check for our values of m and n. The partial derivative of m with respect to y, which is the other variable, is just going to be 10y, and that's it, right? It's just 10y because this thing is just a function of x, and if you derive it with respect to y, if you assume that they are independent of each other, it's nothing, right? On the other hand, right, the derivative of n with respect to x will be, right, this thing has an x, so we just derive that out, and well, this is just a constant, so we derive that out as well. As you can see, both of these would result in 10y. That means that we are good to go for exact equations, right? That means that we are good to go. Now, that is our first step, the derivative step to check. Next, we will go and integrate, right? Which one to integrate? I don't know, right? I'll just choose, say for example, this first one, right? 5y squared plus 6x dx. What will happen is that we just treat this like normal, right? Normal rules apply, and if you have variables, just don't mind them, right? You have other variables, just don't mind them. So in this case, this will just be 5 times x times y squared plus 3x squared, right? Via reverse power rule. And then normally we would write down here a plus c. But in this case, I would like to try it out now that if we derive this, we will put in our c as a function of y. Why is this the case? Because if you think about it, right, your fy in here is not counted, right? It's not counted as a part or as a result of the integration. How can we check if this answer is correct? By deriving it with respect to x. What's supposed to happen, or rather what you're supposed to be able to see, is that if you derive this, any function of y with respect to x, it will just get cancelled because it is not, by definition, a function of x. So this is the way forward for us to just try and account for any quote-unquote excess terms. Now that we have integrated, we will now try and derive it with respect to y this time. Derive it with respect to y. Okay, let's derive this with respect to y. And what we should get is 5xy squared plus 3x squared plus plus f of y. We will get the value of 10xy, right, plus f prime of y. That is the important bit, the prime. And now, as you can see, this seems very familiar. It should be familiar because it's supposed to be an exact match of the other thing, of the letter n, right? Of the expression n. And so this is where our integration factors in at the last moment. The only thing that doesn't match is this matches. The only thing that doesn't match is f prime of y is equal to -4. That means that if this is indeed correct, fy prime is equal to -4, you can just do a simple integration in your head. If f prime is -4, that means that the original function f is just going to be -4y. So that in fact was our original equation, and our original function, and that means we have found our answer. Whatever our answer here was is already the final answer. 5xy squared plus 3x squared plus, or rather minus 4y, and then you write down equals c. Because in this case, what we were doing is basically we were backtracking, right? We were trying to find a way to create something, right? An equation such that if what you're going to do, right? If what you're going to do is going to, you're going to get the total derivative. If you guys remember a total derivative, you would derive the function, right? You would derive the function, whoops, not green. You would derive the function with respect to x, and then you multiply it by dx. You derive the function with respect to y, and then put dy. And then on the other side, because you're taking the total derivative, what is the derivative of a constant? It's 0. That is the motivation behind exact equations, right? So besides, right, the whole very winding path that we take, right, the derivative, and then you turn into integral, and then you turn derivative, and then you turn integral again. That is the motivation, right? We are supposed to backtrack to find a common function equals a constant that when derived will give us these two derivatives, right? These two partial derivatives. Right? That is our first problem. We will have two more. And now in here, no more, what do you call this? No more color coding, right? And now in this case again, right, I would like to remind everybody that this is not, right? This is not a good, what do you call this? This is not a good structure for exact equations. What we should do is instead put this to the other side. We will get something like this is equal to 0. But again, right, this is still not good enough because we need this to be positive. So it should be plus and then negative, and then I will put it like that, and then can it only be a good candidate for, right, for your exact equations. This is your m because it's stuck to the dx. This is your n because it's stuck to the dy. Let's perform a check first. D, right? When you derive m with respect to y, it will just be, this just gets cancelled. So this becomes 2x cosine y. On the other hand, right? Yeah, that's right. And then on the other hand, in here, what we will have is, what is this? The derivative of n with respect to x, sorry. The derivative of n with respect to x will be equal to, well, this will just be 2x, negative 2x cosine y. Now, you might say to yourself, well, it's close enough, right? This is positive, this is negative, this is good enough, right? This is good enough for exact, for exact equations. Actually, no. Right? This thing cannot be part of the exact equations, or you cannot do the same procedure because, well, they are not, by the word, exact. Right? So there is a technique called unexact equations. I will not go into that, right? But there is a technique. If these two terms look similar enough, what you can do is you can go through another step so that they can appear exact. But for now, let's just assume that with the wave of a magic wand, this becomes positive. Right? This becomes positive. Congratulations. This is now a good candidate for your exact equations. Okay? So again, right? Let's try and do this now for the other side, this one. Right? X squared times cosine y dy would just give you, well, you don't mind the x squared, and you will just need sine y, and then, right, you need to account for what you didn't integrate, which was a function of x. Okay, and now we go again and we derive this now with respect to x. Derive this with respect to x squared times sine y plus that function of x that we might have missed, and you will get 2 times x sine y plus your f prime of x. And as you can see, I see. They're similar except for this last one, wherein your f prime of x is just equal to negative 1. Well, oh, sorry, this is positive 1 pala, rather. Right, this is positive 1, therefore, your f of x is just going to be x. That means that your final answer in here is the answer that you're supposed to get from here in the very beginning, which is going to be x squared sine y plus x is equal to c. That is already good enough as a general solution. A general solution. Okay, right? So we can see, right, still very confusing, but hopefully you guys are starting to get the flow of exact equations, right? But as you can see, right, it's not as convoluted or maybe as involved as linear differential equations because of the amount of setup there, right? And now for this last one, we will have something a bit more complicated, right? But still, right, still solvable. And we have once again, the appearance of a boundary condition, right? A boundary condition wherein if you plug in x equals 0, you will get y equals 1. That is what we mean when y of 0 is 1. Now, just to make this very clear, this is our value of m, and this is our value of n, right? And at this point, these two are still not completely expanded. So let's try and expand that now. I'll just rewrite this as 3x squared y minus 3y dx plus, right? And that's good. There's a plus in there because if there were no pluses in there, then that means this is wrong, right? This is not a good enough candidate for exact equations. So let's begin. Let's check this, right? Partial m over partial y will give us basically the derivative of this with respect to y. Well, everything is it just has a y, so it's 3x squared minus 3. On the other hand, your partial n over partial x will be 3x squared. This one gets cancelled, and then this one here removes his x, and now you will see that they are indeed identical. So now I will choose which one I want to integrate. Maybe this one, right? The integral of x cubed plus 8y minus 3x times dy is basically this: x cubed y, right, plus 4y squared minus 3xy. And then we might have missed some value, right? Some function of y. So I will put in here a function of x. So I will put it here. Okay? So hopefully we were able to follow along with that integral. Again, the other variable does not matter, right? It's only y that matters in here. So it's here, and that is why I only added the y for the x cubed and then the y for the negative 3x. Now, what will happen is that I will derive this now with respect to x. Let's see if anything happens. X cubed y plus 4y squared minus 3xy plus the function, the mystery function of x. What we'll see is that this will become 3x squared y. This gets removed. This becomes minus 3y, and then plus that f prime of x. Right? F prime of x. But as you can see in here, well, this is already completely matched with this. Therefore, the only conclusion we can make is that, well, this isn't needed anymore. This is already good as is, which means that our semi-final answer, we're not done yet, is x cubed y plus 4y squared minus 3xy is equal to C. The thing is, before we box this as our final answer, we need to remember that this is still just a general solution. What we need when we are given a boundary condition is the particular solution. So we need to substitute. If x is equal to 0, then y is equal to 1. Well, x is equal to 0, so 0 cubed times 1 plus 4 times 1 squared minus 3 times 0 times 1 is equal to C. These things get cancelled. This gets cancelled. So 4 times 1 squared is just 4. That means that our C is equal to 4 and that our final answer, right, thus, right, our final answer is x cubed y plus 4y squared minus 3xy is equal to 4. This is now our particular solution. Oops. This is now our particular solution. There you go. That is for exact equations, right? This is for exact equations. And well, as you can see, right, it's quite shorter a little bit. The solution is quite shorter, but the problem is, or rather the trade-off here is that you need to remember this flow, right? Derive, integrate, derive, integrate. So later, what you might do is like integrate first and then derive. So hopefully you're able to feel these exact equations out. Okay. All right. So that's it. That is for exact equations, and that is it. If you detect that your differential equation is of the first order, what happens if it's now higher order? We will now, in the next video, look at the differential operator, and after that, we will have the method of undetermined coefficients. So, all right, that will be it for now. I hope you guys learned something. Thank you.